Recording.
All right, so chapter 28. Are you ready, Lemos?
I'm ready.
All right, enriched categories. A category is small if its objects form a set, but we know that there are things larger than sets. Um, yeah, set theory. Weird.
Unpaused.
Uh, yeah, a category is small if objects form a set. We know there are things larger than sets. A set of all sets cannot be formed in standard set theory. This is, well, if you know a little bit of modern mathematics, this should come as no surprise. So a category of all sets must be large. And there are tricks you can do. I think this thing here is actually related to like the way dependent languages model the type.
Oh,
Um,
I didn't know
yeah,
that.
yeah, they have something called cumulativity where the type does not include itself, but there's a type, but that's the type zero, and there's a type one that includes type zero, and you can
Oh,
build a tower. Yeah,
I see what we're doing here.
yeah, that's kind of related to this. Uh, yeah, there are these tricks, and they let us talk about large categories. Categories locally small if morphisms between any two objects form a set, right? Because we've been talking about home sets this entire time, right?
Exactly.
But if they don't form a set, we will have to rethink a few definitions. Um, yeah, and then we have to worry about composition because we can't just pick morphisms from a set anymore, right?
Yes. Yes.
And yeah, so the solution is we replace home sets, which are objects in the set category, with objects from some other category V. In general, they don't have elements, so we can't talk about individual morphisms, and we have um, in this new enriched category, we have to define their properties in terms of like operations on home set objects as a whole. We
I
can't
have a
talk
I have a
about
thing though. My
okay.
feeling reading this is that as we did with monoids before, and we upgraded them to monoid categories, we are kind of doing the same treatment of upgrading and calling that enrichment to any category.
Uh, Yeah, we're basically saying, okay, we're going to take a monoidal category and we're going to use it to enrich another category, which can be arbitrary, basically. Yeah,
Yes.
your sense is it makes sense. It is correct, I think.
Yeah, I have a little bit of doubt on how can this can be applied to programming at all, because in my understanding, programming we are always on the level of sets, so there's no need to abstract that even further. But my understanding is that, well, I think the next chapter will say this as well, which is that we are so far beyond programming at this point.
Yeah, no, we're getting into logic, but although we're not entirely outside of programming because this is actually this notion of like using a monoidal category to define home objects and so composition. This is actually related to concatenative programming as well.
Damn. Okay, that's very interesting. Let's continue.
Uh, if we call this monoidal category V, we can talk about the category C enriched over V, and yeah, we need it to be monoidal. Besides size reason, we might be interested in generalizing home sets to something that has more structure, because sets are kind of whatever, right, in terms of
Mhm.
categorical structure.
Mhm.
For instance, the traditional category doesn't have the notion of a distance between objects. They are either connected by morphisms or not, and every
Yeah.
object that's connected is neighbors with it.
Yeah.
Yeah,
Exactly.
we haven't seen anything about it so far.
Yeah.
There's one more very practical reason to get experience within these categories. That's because of this online resource here. I actually haven't looked at it.
I just clicked
Uh,
on that link, but I didn't dive into it.
yeah, but it's written mostly in terms of enriched categories, which is like, okay. So why a monoidal category? Because, well, let's read it. When constructing the enriched category, you have to keep in mind we should be able to recover the usual definitions when we replace it with set and the home objects with home sets, which
Yeah.
makes sense. We don't want to lose what we already have, right?
Yeah, we are keeping what we had and basically abstracting, making it even more generic, I guess.
Yeah. And the best way to accomplish this is to start with the usual definitions and keep reformulating them in a point-free manner.
Yeah.
And you can kind of see where this is going, right?
Yes. Yes. 100%.
That is without naming elements of sets. So we start with composition. Normally we have a pair of morphisms, and we have this mapping between these two morphisms and this third one.
Yeah, but here's the
And
thing though. This is a function that grabs two home sets, right? We have a home set of all the morphisms going from B to C, and we're making that a product with another home set that contains all the morphisms from A to B.
and we are going from that to another home set from A to C.
Yes. Like this is what we mean by like we are we are we are talking about all the available morphisms between the elements. We're not talking about individual morphisms anymore.
Yeah. Uh, this is a function between sets, one of them being the Cartesian product of two home sets, which is this one.
Yes.
This can be easily generalized by replacing the Cartesian product with something more general. A categorical product would work, but we can go even further and use a completely general tensor product, which is something we've seen a while back, actually, right?
Yeah, that's I did some revision before the session, and a tensor product is basically a particular property of a monoidal category that has a bifunctor thing.
Yeah, it's basically a generalization of a normal product. Technically, sums also qualifies as tensor products because, like, although sums and products are kind of different in how they behave, like their actual structure, like
Mhm.
the categorical structure is pretty similar. They are both bifunctors.
Mhm.
Next come the identity morphisms. Instead of going from individual elements, we use functions from the singleton set, but we can replace it with the terminal object, or we can go even further and replace it with the units of the tensor product, which actually varies depending on which tensor product you're talking about.
Can we talk about why the JA is replacing identity for a moment? Why is that the new identity exactly?
Because we have to define the identity in terms of, well, we can't talk about individual morphisms anymore, so we need to talk about a relation um,
Sets.
well, yeah. And basically, instead of just saying C from each way, if you want to talk about it in terms of category theory, right, because we're going over a monoidal category, this
Mhm.
better be a morphism, ideally, because we can't speak inside of objects anymore.
Mm. Okay, I see. So that's why we need the singleton.
Yep.
Okay.
As you can see, objects taken from some monoidal category V are good candidates for home set replacement. And then we talk about monoidal categories a little bit. We've talked about them before. It defines a tensor product that is a bifunctor with this signature. We want it to be associative, but it's enough to be associative up to natural isomorphism. And this is called the associator, and its components are, well, technically there's the one
There,
going backward from this as well, right?
yeah, and there are the lambda and the whole as well.
Yeah.
Mhm.
Yeah, but basically this is like, so it's an isomorphism that basically says, hey, associativity, but only if you go through this isomorphism. It's not true associativity, I guess. It must be natural in all three arguments, natural in the sense of being functorial. The monoidal category must also define a
Wait,
special.
why are the three arguments natural? And they need to be.
Like, you know how, because they need to be, because otherwise you won't be able to talk about all three of them separately.
Mm. Okay. Okay.
Um, Yeah, otherwise we would be stuck in the situation with those di-natural transformations, right? Where you only deal with diagonals, and we don't want that in this case.
Yeah, I don't remember dynamic transformations anymore, but I think we can go further.
A monoidal category must also define a special unit object I that serves as the unit of the tensor product, again up to natural isomorphism. And there are two isomorphisms called the left and right unitor, and they are this.
Mm-hmm.
Yeah, basically eliminating the left and right identity elements.
Yes.
And the associator and the unitors must satisfy these conditions. So um, basically, this one is about being able to reassociate when you have four things, right?
Mm-hmm.
Three with three tensor constructors, four types, four leaf types, I guess. And this other one is for um, associativity in the presence of the unit
Unit.
here.
Mm-hmm. Mm-hmm.
Um,
And
yeah,
then you
basically,
talk
if you have the
about being
unit,
symmetric. Mm-hmm.
yeah, basically you can remove the unit from between two things, and this. If you start from here, you can go all the way here
Yeah,
in two
basically.
different ways.
Yeah, these are basically the same things as monoids, but we are looking at them from a like making a category on top of them, like we did with monoidal categories before. I
Yep.
really don't see why. Like, I lied. I do see why we would do this, but it's so much more natural to me to talk about monoids in the other previous known upgraded way.
Uh, One thing that's not in this picture is that because this A is a natural isomorphism, this diagram you can also flip all the arrows, and it still must hold. So
That makes sense.
um, yeah, and technically this one should also be flippable. I don't know why they didn't mention the introduction of the tensor unit, because that's technically a thing. Although I don't think for defining composition though that would be necessary. So I guess that's why.
Mm-hmm.
Monoidal category is called symmetric if there's this natural isomorphism like this, which is basically commutativity, right? That's optional for monoids.
Mm-hmm.
Uh, and the commutativity needs to be its own inverse, basically.
Yeah.
And consistent with the monoidal structure. Um, you may be able to define the internal home the object as the right adjoint to the tensor product. This has to do with currying, right?
I don't
Um,
recall these right and left adjoint things of the tensor product. Is that because of currying? Are you sure?
yeah, I think so. You may recall that the standard definition of the function object, or the exponential, was through the right adjoint to the categorical product. Yeah, this is totally currying. A category in which such an object existed for any pair of objects was called Cartesian closed. And here's the adjunction. Um, Following G and Kelly, using the notation with square brackets B, C for the internal home, I guess it would be equivalent to having a narrow type in Haskell, I guess.
Wait, but what do? Can we go backtrack a little bit and talk about what is the internal home in there?
Uh, it's basically it's basically a home object that exists inside of the category.
Hmm. The function object. You said arrow type, right?
Yeah, basically an arrow type, essentially.
Oh, this is why you said it's currying.
Yeah,
Okay, I see.
yeah. See, this goes from taking the tensor product and returning C to taking an
Yeah,
A and
returning a
returning
function.
a function from B to C.
Yeah, makes total sense.
Following GM Kelly, we're using square brackets for the internal home, which is like, okay, I guess. The co-unit of this adjunction is the natural transformation whose components are called evaluation morphisms, which is basically apply, I guess.
Yep.
Notice that if the tensor product is not symmetric, we may define another internal home denoted by double square brackets using the following adjunction. So taking a B and goes to C from taking a B and returning an arrow from A to C. So like filling in the right parameter first instead of the left one, I guess.
Wait, your internet went a little bit bad during that explanation. Can you repeat the last part?
Okay, so if the tensor product is not symmetric, there's another internal home with double square brackets, which basically like flips the order of the arguments when you curry.
Flip the order of the arguments, you say.
Yeah, see, the normal one takes A and B and goes to takes an A and return an arrow taking a B, right?
Mm-hmm.
But this one is backwards. It takes A and B, but it goes to taking a B and returning an arrow from A to C.
What is the semantics of the double brackets?
Well, it's basically a flip combined with what is it? Uncurrying.
Wait, do you mean flip as the flip function?
Yeah, and this is like if only if the tensor product is not symmetric, apparently, because otherwise, well, because otherwise you can just use this
Wait, so
instead.
so what you said down there is a function from C to A? Is that what you're saying?
No, no, it's a function from A to C, but it's curried in a way that it binds the left argument after the right one.
Ah, I see what you're saying. Okay, I see.
Uh, yeah, right, because I guess you need this if it's not symmetric because you wouldn't have access to this, right?
Yes.
Makes sense. Another category in which both are defined is called biclosed. An example of a category that is not biclosed is the category of endl functors in set, with functor composition serving as the tensor product. And it's the category we use to define monads, which is okay, I guess. So
Wait,
in rich
wait, go
category,
scroll up a little bit again.
okay,
An example of a category that is not by close is a category of endl functors in set, with functor composition serving as tensor product. Wait, another category in which both are defined. Both what? Do you mean the both adjunctions?
no, both the evaluation morphism and this secondary tensor product.
That is called a biclosed monoidal category. An example of a not biclosed category is the category of endl functors in set with functor composition serving as tensor product.
I may
That's a
be interpreting that paragraph wrong though.
I don't know. Which we are talking about the
Yeah,
monoidal category that we use to define modes, right?
yes.
We are saying that that category is not biclosed, which means that the category doesn't have the adjunction.
Well, I guess it
Uh,
wouldn't have this one because it certainly had this one, right? And it certainly had
apply.
did it have this? Yeah, but not this, I don't think.
Oh, okay, so that's why it's not biclosed because if you have both, you are biclosed.
Yeah,
Okay,
I think so.
we can proceed.
In which category? A category C enriched over a monoidal category V replaces home sets with home objects. And to every pair of objects A and B in C, we associate an object using the same notation, no risk of confusion in V.
Yeah, that's exactly what I thought when I was reading this. To every pair of objects A and B in C, we associate an object C, A, B in V. We use the same notation as used for home sets with the understanding they don't contain morphisms, with no risk of confusion at all. Again,
Yeah, yeah. On the other hand, V is a regular, non-enriched category with home sets and morphisms, so we're not entirely rid of sets yet.
yeah.
They're
So
just under the
it's kind of
rug.
like on the category C, we wanted to get rid of those, and we did by enriching it with V. But V itself can still be talked about in the terms that we just excluded from the other one.
Yes.
So it's like Inception.
uh, yeah, not sure how much I like this one because, like, you're trying to get rid of sets, right? Because category theory, but you didn't. That's kind of sad. Since we cannot talk about individual morphisms in C, composition is replaced by a family of morphisms in V, which have this signature, I guess.
Which is basically like those home sets are basically objects in V, right? So this is
Yeah,
basically a morphism from a pair to another object.
yep.
Yeah. Okay.
And they are denoted by these fat arrows, I guess.
Fat. Yeah. That. How do you call this? Because they're not fat all the way. They have skinny heads and skinny bottoms, but they are fat in the middle.
I guess they are bloated, I guess.
Bloated arrows, even better. Okay.
uh, Similarly, identity morphisms are replaced by a family of morphisms in V with this signature, where I is the tensor unit. Um, and it's like this weird, like crescent moon shape, I guess.
Bloated.
Associativity of composition is defined in terms of the associator. So, normal associativity of composition, I guess.
Mm-hmm. Mm-hmm.
And unit laws are likewise expressed in terms of unitors. So this, if you apply the unitor here, you can apply the composition to get to here, which is the same as this.
Yep. That makes sense.
And likewise for the case where the unit is on the left. And now we're back to pre-orders again.
Yeah, now we're going to go through some examples on how we can interpret previous understood problems using this view of enriched categories.
Alright, so a pre-order is defined as a thin category, one in which every home set is either empty. We interpret a non-empty set as the proof that A is less than or equal to B, and with A being on the left. Such a category can be interpreted as enriched over a very simple monoidal category that contains just two objects, 0 and 1, sometimes called false and true. So freaking booleans.
Off the course,
Uh,
off the course.
Besides the mandatory identities, this also has a single morphism for going from 0 to 1. Let's call it 0 arrow 1, which is an okay name, I guess. Simple monoidal structure can be established in it, with the tensor modeling the simple arithmetic of 0 and 1, i.e. only the non-zero product is 1 times 1.
Mm-hmm.
The only non-zero product. The identity object in this category is 1. This is a strict monoidal category, that is, the associator and the unitors are identity morphisms. Okay, and then since in a pre-order the home set is either empty or a singleton, we're going to replace it with a home object from our tiny category. It has a home object this for any pair of objects A and B. If A is less than or equal to B, this object is 1, otherwise it's 0. So
Yeah. This what we're doing here is basically the following. We created there is some renaming operations going on because if CAB, although the notation is the same, no risk of confusion, this is not a home set. This is an object. It just so happens that if this object exists or not, we are denoting it a different name for it. So if the object CAB contains one morphism from A to B, we are renaming CAB as 1. And otherwise, if this is empty in its home set form, we're going to rename the object as 0.
which is a very roundabout way of defining a predicate, I guess.
Well, that's what we're going to talk about in the next chapter.
Yep. Let's have a look at composition. The tensor product of any two objects is 0 unless both of them are 1, in which case it's 1. Basic Boolean algebra, right? If it's 0, then we have two options for the composition. It could either be identity at 0, or you can go from 0 to 1. But if it's 1, the only option is this. So translating this back to relations, if this says that if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C, which is exactly the law we need. And for identity, it's a morphisms from 1 to the number, it's the object itself, right?
Mm-hmm.
Because, well, there's only one morphism going from 1, and that's the identity, so this must be 1. So this means that A is less than or equal to A, which is the reflexivity
Reflexivity.
law.
Mm-hmm.
So both laws are automatically enforced if we implement the pre-order using an enriched category.
I have a question, which I think is a dumb question. Can you scroll up a little bit?
Okay?
Yeah, here. Let's. I want to take a look again at composition. So it's saying that the tensor product of any two objects is zero unless both of them are one, in which case it's one.
Yeah.
Um, why that's the case though?
Why is that the case?
Yeah, if you do a
Um,
tensor product of two zeros, that means that we have two objects in which both of them are zero, which means that both of them there is no pre-order relation going on, right?
right.
So what are we calling tensor product in this context?
Uh, I
Uh,
guess you could try. I guess you could consider it a pair, essentially, in this case.
mm. I was with a feeling that the product is the composition itself.
Well, it's being used to define the composition in the C category, but inside of V, it's basically a pair.
Okay. So then we go further and talk about if they are mix matched, which is that one of them is zero and the other one is one, or vice versa.
Well, if you consider 0 to be like void, which cannot be instantiated, and 1 to be unit, which can only be instantiated one way, right? That's
Mhm. 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 Mhm.
then if you have a pair where one element is void, it cannot be instantiated, right?
Yes.
So you can only get back to a unit if both sides of the pair are units.
No, that makes sense, but I'm talking about the next sentence. If
If
it's
it's 0,
zero, then we have two options for the composition morphism. It could be either 0 to 0 or 0 to 1, right?
right?
But if it's 1, then the only option is identity 1. And that's not my question. We cannot go from 1 to 0 then. We need to go 1 to 1
Yeah, we cannot go from 1 to 0, basically.
because of what you just said, I guess. Because you could not be able to instantiate a void.
Yep.
Okay, okay, I'm convinced. Okay, metric spaces. So just a curiosity, being my
Okay.
master's, because I had to study fixed point combinator, metric spaces, they have a theorem called the Banach theorem. I don't know how to pronounce that exactly.
It's probably Banach, right? It ends with a ch, which is
Yes.
yeah, it has a weird pronunciation.
Yeah, which talks about it's a theorem that talks about contraction mappings, which is a concept within the domain of metric spaces. And I think this prelude that we have in the first paragraph, I think it's pretty much on spot on. Metric spaces is all about defining distances, um, and there's many mathematical things going on in that space, and fixed point is just one of them.
Uh, yeah.
I think we can jump this paragraph because it's basically explaining that where a metric space defines the distance between any two objects, and then we want they need to be non-negative, of course, because there doesn't make sense to talk in distance in terms of negative numbers at all. And
Uh,
you can have
I
a
mean, you could. I
yes,
mean, you could define a displacement which can be negative, but that's not the same thing as distance, right?
yeah, no, yeah, displacement is a different thing. And if you have a very big distance, we can basically define say that they are far from each other. And what we're going to do here is basically to use the enriched categories terminology to explain or to model these metric spaces. So I can read this one. There are some obvious
All right.
properties that have to be satisfied by distances. One of them is that the distance from an object to itself must be zero. That makes sense. There is a triangle inequality. The direct distance is no longer than the sum of distances with intermediate stops. We don't require the distance to be symmetric, which might seem weird at first, but as explained, you can imagine that in one direction you're walking uphill while in the other one you're going downhill. In any case, symmetry may be imposed later as an additional constraint. Wait. Let's just reinforce the inequality thing because I think it's important. The direct distance is no larger than the sum of distance with the intermediate stops. This kind of sounds obvious, right? Like if you have a distance of 5, uh, that should be equal to the sum of doing intermediate stops between the 2 points, such as 1 and 4, and 2 or 3, or 3 and 2. Uh,
Yeah, but here it's not saying it has to be equal. We just have to not be larger, right?
yes, it doesn't have to be equal. Well, in my example, it needs to be equal, right? Because it doesn't make sense. But what it's saying is that the direct distance is no larger than the sum of distances with intermediate stops. How can
Yeah,
we have an example though in which the direct distances? Oh, it's because it may not be optimal, right? The intermediate stops. Then the
right.
direct distance may be smaller than the sum, right? It wouldn't require the distance to be symmetric. So anyway, we can continue now.
All right. So how can a metric space be cast into a categorical language? We have to construct a category in which the home objects are distances. Mind you, distances are not morphisms, but home objects. How can a home object be a number? Only if you can construct a monoidal category V in which these numbers are objects. Non-negative real numbers plus infinity form a total order, so they can be treated as a thin category. Um, yeah, adding a point to represent the points where parallel lines meet is something convenient to do in some forms of geometry.
Mhm.
Uh,
Mhm.
a morphism between two such numbers x and y exists if and only if x is greater than or equal to y. Note this is the opposite direction to the one traditionally used for preorders.
Yes.
And then the monoidal structure is given by addition with 0 serving as the unit. In other
Yeah, I think
words,
we saw this when we talked about monoids the first time. I think this entire distance and understanding of between 2 points, we used the same explanation to understand monoids before.
yeah,
Like in chapter, I don't know, 4 or 5 or whatever.
yeah, we did. I mean, it's the one that most people would be more immediately familiar with, right? Addition of numbers.
Well, you're right, but I don't know. I like the string example better.
Yeah, the string example is better because it shows that it may not be commutative, right? With numbers, you may be misled into thinking that
Yes.
monoids can be commutative.
No, not that they they
Or
they
rather,
must
they
be,
are
right?
required, right? They
Yeah,
don't
exactly.
have to be commutative. They might
Exactly.
be, but not necessarily.
Exactly. I agree with that.
So a metric space is a category enriched over such a monoidal category. A home object from objects A to B is a non-negative, possibly infinite number that we will call the distance from A to B. Let's see what we get for identity and composition. So,
Yeah.
bar definitions, morphisms from the tensorial unit, which is 0, to a home object is this relation.
Yeah.
Um, since this is a non-negative number, this condition tells us that the distance from A to A is always 0. Check. Now, composition. We start with the tensor product of two abutting home objects, C of BC and C of AB, and we have defined the tensor product as the sum of the two distances.
Yes.
And then composition is a morphism in V from this product to CAC. And a morphism in V is defined as the greater or equal relation. In other words, the sum of distances from A to B and from B to C is greater than or equal to the distance from A to C. But that's just the standard triangle inequality.
Yep.
So check. And by recasting the metric space in terms of an enriched category, we get the triangle inequality and the zero self-distance for free, quote unquote.
Yeah, so here's something very important to say here. What we are doing with the enriched categories approach is basically defining a framework in which you can describe other types of phenomena and you reach the same kind of conclusions that we use different methodologies to achieve, but with a single uniform approach. So we just did with pre-order, now we did with metric spaces. What else from different areas can we use this approach to that will work magically?
Uh, a lot of things, I would think.
No, yes, I'm not saying that we should list them. I'm just saying that this kind of trick is kind of cool because uh, let's say that you have a problem that you are having a trouble in identifying its properties. If you may try to rewrite the problem using this terminology, and if you can, you actually can deduce the conclusions in the framework and then try to understand what they mean in the domain of the application.
Right. Um, Enriched functors. So the definition of a functor involves a mapping of morphisms. And the enriched setting, we don't have the notion of individual morphisms, so we have to deal with home objects in bulk. They are objects in category V, and we have morphisms between them. So it makes sense to define enriched functors between categories when they are enriched over the same monoidal category V. And then we use morphisms in V to map the home objects between the two enriched categories. So yeah, functors have to use the same V um, for both the source and the destination, I guess.
So these are Indo functors.
Not really, because the category that is enriched over V may be different, right?
Oh, okay, that's true. That's true.
So an enriched functor F between two categories C and D, besides mapping objects to objects, also assigns to every pair of objects in C a morphism in V. No risk of confusion whatsoever.
Well, but in this case, kind of makes sense, I would say. Like, assuming that we are not confused by the use of the double notation for home sets and home objects, this kind of makes sense to me after accepting that no risk of confusion.
Yeah, no, it does make sense. It's just, it's even more overloading, I guess.
It's even more overloading. I agree with that.
A functor is a structure preserving mapping. For regular functors, it meant preserving composition and identity, and in the enriched setting, the preservation of composition means that the following diagram commutes. Um, so basically, if we have a pair
This
of
tensor
functors,
product,
these
and then
tensor products,
you compose, you get what you would expect. If you lift the tensor, you get a tensor of the applied functors within.
within D,
Uh,
because it's a
uh,
functor from C to D,
yes, and
and this must be the same as applying the functor pointwise to the tensor product first, and then
yes,
composing.
exactly. Uh,
Uh,
yeah, makes sense.
the preservation of identity is replaced by the preservation of the morphisms in V that select the identity. So
Yeah.
yeah, if you have G of A, G at A, J at A, and J at FA, then FAA needs to go from one to the other.
Mhm.
And then self-enrichment. A closed symmetric monoidal category may be self-enriched by replacing home sets with internal homes, which you saw the definition above. And to
Yes.
make this work, we have to define the composition law for the internal homes. In other words, we have to implement a morphism with this signature.
Which is basically just composition, right? At this point.
It is basically just composition, yes.
Uh,
This is not much different from any other programming task, except that in category theory, we usually use point-free implementations. We start by specifying the set, whose element is supposed to be. In this case, it's a member of this home set. Uh, yeah, from the pair to the composition in V, which is isomorphic to this. This is just anchoring.
wait. I had to sniff, so I lost the plot. Can you go back a little bit? So we start by specifying the set whose element is supposed to be. In this case, it's a member of the home set.
This one in V, which V still has a home set, if you recall.
Yes, yes. So we have a function We have a tensor product of two functions and another function on the other side. Okay. And the home
which
set
is,
is isomorphic to
yeah, this is just
which
uh, anchoring basically.
this is
Yeah.
yeah, it's kind of crazy that yeah, but what does that mean though? Oh, wait, the comma. I see. So, yeah, this is anchoring. Yes, yes.
Yeah, this the A went to the left of this comma here.
Yeah. It's kind of crazy how many notations we have now learned that all of them mean anchoring.
Yeah, it kind of is.
Okay.
Uh, so I just use the adjunction that define the internal home. If we can build a morphism in this new set, the adjunction will point us at the morphism in the original set, which we can then use as composition. We construct this morphism by composing several morphisms that are at our disposal. To begin with, we use the associator to reassociate the expression on the left. Um,
Yeah, this is just associativity.
yeah, moving the parentheses over here. Then we follow it with the co-unit of the adjunction, which is apply, basically, right?
Yes. The dollar.
The dollar. Then we use the co-units at BC again to get to C, because we have a B now. And we have thus constructed this morphism, which is this thing after this thing after this thing, which is, yeah, lots of subscripts, I guess.
That's a salad of letters.
Yeah, it is. And this is an element of this home set, and the adjunction gives us the composition we are looking for. Similarly, this identity is a member of this home set, which is isomorphic through adjunction to this. Uh, we know this contains the left identity, so we can define J at A as its image under the adjunction. Because, yeah, right, because lambda A can just get rid of this I, and then we just have V
A.
from A to A.
Yeah.
A practical example of self-enrichment is the category set that serves as the prototype for types in programming languages. We've seen before that it's a closed monoidal category with respect to Cartesian products. In set, the home set of any two between any two sets is itself a set, so it's an object in set. We know it's isomorphic to the exponential,
Yes.
so the external and the internal homes are equivalent.
What are external homes though?
Because there may be some categories where the home object is not inside of the category.
Uh, no, but that how can that be though? My understanding is that the home objects are always over in V. Am I crazy?
Like, there can be a category where you cannot build function objects inside of the category, basically.
Can you give an example of that?
Pre-orders.
You cannot make a functional object. You said.
Yes.
Okay. Okay.
We also know that through self-enrichment, we can use the exponential set as the home object and express composition in terms of Cartesian products of exponential objects.
Yeah, I don't know if I follow all of that. That we can use the exponential set as the home object and express composition in terms of Cartesian products of exponential objects. I don't know if I follow all of that.
Exponential set is the set of all the subsets of a set, if I'm not mistaken.
Wait, repeat that.
If I'm not mistaken, the exponential set is the set of every subset of a set.
Oh, okay. I think that makes sense for the Cartesian products, I guess. Mhm. Okay.
Yeah, I think this is more commonly called the power set instead.
Mhm. Okay.
Relation to two categories. Two categories in context of cats. The categories small categories. The morphisms between categories are functors, but there's an additional structure: natural transformations between functors. In a two category, the objects are often called zero cells, morphisms are one cells, and morphisms between morphisms two cells. We've seen this before, right?
Yes.
So in cat, those are categories, functors, and natural transformations. But note that functors between two categories form a category too. So in cat, we really have a home category rather than a home set.
That
It
functors
turns
between
out,
two categories form a category 2. So in cat, we
yeah,
really have a home category rather than a home set.
yeah, because there is the category of functors, right?
Yes. Okay, okay, I see.
So it turns out that just like sets can be treated as a category enriched over sets, cats can be treated as a category enriched over cat. Even more generally, just like every category can be treated as enriched over sets, every two category can be considered enriched over cat. And this is the end of this chapter. We're going to do 29 as well, but I just want to mention, I told you a couple times that this relates to concatenative programming, right?
Yeah, I don't see how, and if you can give us any foreshadowing of that.
Basically, you are defining composition in terms of a monoidal structure, right?
Yeah, but what does that have anything to do with concatenative exactly?
Well, in a concatenative language, uh, concatenation is composition, right? And concatenation, if you think about strings, it also applies to the code of a concatenative language. Concatenation is a monoid.
But that I don't understand. That is always the case, no? Concatenation is always a monoid.
It is, but that's kind of the point, right? Because you have this monoidal structure, which is essentially building up. Like if you don't use the V category here, if you just use like chains of pairs, I guess, you can think of that as being equivalent to a list up to isomorphism, right? Because of the
Yes.
associator.
Yes.
But then that means that composition is defined as list concatenation.
Wait, what you said I didn't follow. So you were saying that composition in those terms would be least concatenation?
Yeah, yeah. If you use as V a category where the objects are lists of primitives, I guess, and the primitives can be whatever, depends on what language you're building, then composing those primitives is basically equivalent to list concatenation, right?
Hmm. Yeah,
Well,
I
not
guess so. But it's a really weird notion though, because the composition is just gluing
yeah,
things
because it
together.
yeah, because that's what the concatenative language does, right? If you want to concatenate two functions, you just glue them together, like literally one after the other.
Hmm.
You can think of a function in a concatenative language as being just a list of operations, of primitive operations,
Huh.
and
I
then
think I see.
yeah, and then composition is just concatenation of those lists.
Mhm. Okay.
Yeah.
Okay. I think that's fair. Oh, I will do the 29.
All right. Do you want to share your screen so you can
Yes.
control your scrolling?
Yes, I will share my screen as well.
All right. I will
So there
stop
it is.
sharing.
Okay. So chapter 29. We have a little bit 11 minutes to talk about this. So this chapter is really interesting. This chapter is really cool. It's short, which is why we're combining them together. But the what's happening here is that the author acknowledges that we went too hardcore into the math of stuff, and programming is a little different than that because in programming we compute stuff, like we compute values, and this is going to matter later at the end of the chapter because some computations might not terminate. And this is a common fact, common knowledge in any Turing complete language. Um, So this comment here, I also think it's important to highlight. There are also foundational reasons why set theory might not be the best fit as the basis of computer science, because we're now talking about the differences between the math that we were diving into in computer science. A good analogy is that of set theory being the assembly language that is tied off to a particular architecture. If you want to run your math on different architectures, you have to use more general tools. And then one possibility is to use spaces instead of sets, and spaces come with more structure and may be defined without recourse to sets. But of course, if you're going to talk about spaces, we're going to have to talk about topology and the notions like continuity. And the conventional approach to topology is usually based on set theory. Um, so, and this is the central pillar of this chapter, as far as I remember, which is the notion of a subset is central to topology. Not surprisingly, category theorists generalize the idea of categories other than set. The type of category that has just the right properties to serve as a replacement for set theory is called a topos, and it provides, among other things, a generalized notion of a subset.
Right, because if you're studying spaces, right, it makes sense to ask, okay, I have these two spaces. Is one inside of the other, right?
Yes, so you need to define a notion categorically on what does it mean to be a subset, which is why I think it's so freaking cool. Like, this chapter is, I don't see why it's to the 29th. This could be have talked about way earlier, especially when we talked about injective functions, because it doesn't really rely on all of the notions that we established so far. But it's cool on its own way. So here's the goal of this chapter: is to establish a description in category theoretical terms that we can talk about if something is a subset of another thing. So that's really important. So we're going to go back to functions to talk about this. So any function f from some set A to B defines a subset of B that the image of A under f, right? So we're going to see some images about this, but this makes sense. But there are functions that
Yep.
define the same subset, right? So you may have uh, the intersection of subsets that are being mapped by two different functions such as f and f prime. To begin with, we might focus on functions that are injective, and the reason is because then they will not smush multiple elements into one.
Yep.
Injective functions inject one set into the other. For finite sets, you may visualize injective functions as parallel arrows connecting elements of one set to elements of another. Pretty standard so far. Of course, the first set cannot be larger than the second set because of otherwise they would converge at some point. The
Yeah,
arrows.
pigeonhole principle, essentially.
Sorry,
It's the pigeonhole principle, essentially.
uh, I didn't know that principle has a name, but that's cool.
Yeah, if you have objects and you wanna distribute them over slots, if you have more objects than slots, then necessarily you have to
Yes,
allocate at least
yes.
two objects to the same slot.
And there is some ambiguity left. There may be another set A prime with another injective function f prime from that set to B that picks the same subset. But you can easily convince yourself that such a set would have to be isomorphic to A. That is true. We can use this fact to define a subset as a family of injective functions that are related to by isomorphisms of their domains. And it's a lot of words, but I think the imagery is pretty good. So we're gonna just follow along. So let's suppose that we have two injective functions, f and f prime, in which the domains of f and f primes are different, but the codomain is the same. And we are also imagining that these particular two functions are mapping the same subset. And then
Up to
we,
isomorphism, yeah.
no, these are doing that.
Oh, right, right.
But what is up to isomorphism is the fact that you can map the domains of them to each other. And then we can just say that you can construct f using f prime, assuming that you have h available.
Yep.
And then this is the imagery. So basically, what we're saying is, if you have the domain of a's and the domains of a primes, and you apply the corresponding functions, you're going to go to the same subset in B, and you can move along these domains using H, which I think is a pretty fair way to represent this in a pictorial manner. So now this definition can be lifted to an arbitrary category if we replace injective functions with monomorphisms. A monomorphism M from A to B is defined by its universal property. For any object C and any pair of morphisms, so such as this one, such that. So we're basically saying that if you pick, if this equality holds, assuming this being the case, M is a monomorphism, and it must mean that G is equal to G prime, basically. So this is basically what this is. Again, very well good um, representation, which is that if you have two functions that go from the same domain to the same codomain, and that codomain is M that goes to a subset in B, and M is a monomorphism, that means that G is equal to G prime. That's
Yep.
basically what's being done here. On sets, the definition is easier to understand if you consider what it would mean for a function M not to be a monomorphism, and I agree. What would that even mean? It would map two different elements of A to a single element of B, but that's a problem, right? By premise.
Yep.
But that would mean that we are converging stuff. We are smooshing stuff, as it was said before.
Yep.
Because that would be the imagery here. So you have G and G prime going, pick an element from C, going to A, and then applying M on this A domain to B. It is doing a conversion here. We could then find functions that differs only on those two elements. The post-composition with M would then mask this difference. Yeah, so we would basically be saying that X and Y are different because we are saying that G and G, we are trying to say that G and G prime are not the same.
Yeah.
But M would mask this difference, which cannot be the case because we are assuming that these are injective. There's another way of defining a subset using a single function called the characteristic function. It's a function X from the set B to a two-element set omega.
That's not an actual X, by the way.
How do you call this then?
Uh, I think it's called key or something. Uh, it's a weird letter.
Okay. Anyway,
It's
uh,
it's this letter.
okay. I'm gonna keep calling it X for now. Wait, you said what's the name you said for this one?
Apparently, the
Chi.
standard English pronunciation is. Well, there are two pronunciations actually. Yeah.
Chi.
Yes.
Okay, so chi it is. One element of this set is designed as true, and the other was false, which means that this function is a predicate.
Yep.
This function assigns true to those elements of B that are elements of the subset, and false for those that aren't. It remains to specify what it means the designated element of chi of omega is true. We can use a standard trick. Use a function from a singleton set to omega. We'll call this function true. So there is a singleton set, which is a set with a single element. And we're going to call true the morphism that goes from that set to omega, in which omega being a two element set.
Yep.
These definitions can be combined in such a way that they are not only define what a sub-object is, but also define the special object omega without talking about elements. The idea is that, well, it's a little bit not the case because we talked about elements, right, of omega. Omega is a set with two elements, true and false.
Yeah, but we're trying to not talk about them, basically.
The idea is that we want the morphism true to represent a generic subobject. In set, it picks a single element subset from a true element set omega. Uh, in set, it picks a single element subset from a true element set in omega. This is as generic as it gets. It's clearly a proper subset because omega has one more element that's not in that subset, which is the case. If you are false, you are false and not true, and vice versa. In a more general setting, we define true to be a monomorphism from the terminal object to the classifying object omega. But we have to define the classifying object. We need a universal property that links this object to the characteristic function, which is the predicate in this case. It turns
Yep.
out that in set, the pullback of true along the characteristic function chi defines both the subset A and the injective function that embeds it into B. And here's the diagram. So what we're saying is the following. If you have, we have our function f from before, and then we are trying to specify the notion of a subset.
Yep.
We are trying to express the idea. What would that be? That uh, the object f of A is a subset of B, I guess. Is that what you're trying
Yeah.
to say here?
That is indeed what we're trying to say.
Then, if you pick B and apply chi, you're gonna get to omega because it's a function from the set B to the true element set omega. You have the unit, which basically puts us at a singleton set, and you also have true, which means that you can always go from the subset from the singleton set to the omega set, and then we get this commutativity.
Yep.
This function maps every element of A to true, which is true,
Which is
because this predicate always evaluates true, basically.
yep.
Therefore, F must map all elements to A to those elements of B. So therefore, F must map all elements to A to those elements of B for which chi is true. Because again, this branch here, Marinho cannot see my mouse. I keep forgetting about that. But the true after the unit branch maps every element of A to true.
Yep.
And that means that F must map all elements of A to those elements of B for which chi is true. These are, by definition, the elements of the subset that is specified by the characteristic function chi. Yeah, so I think we need to go a little bit slower on this one because one branch is basically saying that all elements of A are true because the predicate is basically true for everyone.
Yep.
But what the other branch is saying is a little bit different, which is that in order to reach omega, chi is doing a filtering process.
Actually, F is doing the filtering process. Well,
Uh,
kinda. Well, both of them together are doing the filtering, actually.
yes, exactly. Both of them are doing the filtering, but chi is a function from the set B to the true element set.
Yeah, it's a
Uh,
predicate. It can return either true or false, but then for it to always be true, you need to put an F before it
yes,
that
yes. So it's kind of the
selects.
combination of them.
Yeah.
So the image of F is indeed the subset in question. Yes, the universality of the pullback guarantees that F is injective. I have a question though. I have a little bit of a question. Uh, let's suppose that F is also providing as the imagery of A elements in B that are not a subset, part of the subset. Chi on that case would map that element of B to false in omega, right?
Yeah, then that would not satisfy this diagram, basically.
Well, but why that's the case though? We are going to omega, we're just not going to true. The element true inside omega.
But because then you don't have like you don't have if you actually look at the actual, what can I say, like you could be able to construct another morphism that goes after, like that takes the omega and goes and does something that could distinguish between the two, essentially.
Yeah, but what's the problem with that in that case?
Well, um, you're not actually defining the correct subset.
Oh, okay, I see why. Okay, it's kind of what you said. It's because this part of this equality is assuring us that we need to go to true on omega.
Yeah,
Okay. The universality of the pullback guarantees that f is injective. Yeah, because otherwise we would be doing the conversion thing again.
yep,
The pullback diagram can be used to define a classifying object in categories other than set. Such a category must have a terminal object, which will let us define the monomorphism true. It must also have pullbacks. The actual requirement is that it must have all finite limits. A pullback is an example of a finite limit. Under those assumptions, we define the classifying object omega by the property that for every monomorphism f, there is a unique morphism chi that completes the pullback diagram. So we're basically saying that for every available function f, you will always be able to go to the true or false set.
basically.
Let's analyze the last statement. When we construct a pullback, we are given three objects, omega, b, and 1, and two morphisms, true and chi. The existence of a pullback means that we can find the best such object A, equipped with two morphisms f and unit, the latter is uniquely determined by the definition of the terminal object, and make the diagram commute. Here we're solving a different system of equations. We are solving for omega and true when varying both A and B. For a given A and B, there may not be a monomorphism A to B. But if there is one, we want it to be a pullback of some chi. Yes, of course, because these, if like, if you, there's no guarantee that there is a morphism between these two. But if there is, we want to add some constraints on top of it. Moreover, we want this chi to be uniquely determined by f. We can say that there is a one-to-one correspondence between monomorphism f and the characteristic functions chi, because a pullback is only unique up to isomorphism. But remember our earlier definition of a subset as a family of equivalent injections. We can generalize it by defining subobject B as a family of equivalent monomorphisms to B. This family of monomorphisms is a one-to-one correspondence with the family of equivalent pullbacks of our diagram. So basically, uh, how can I summarize this?
We're,
Uh,
we're trying to define subsets categorically, essentially.
yeah, no, yes, but we said this before. I'm just talking about this particular paragraph. Uh, I think that's it. We can thus define a set of sub-objects of B, sub B, as a family of monomorphisms and see that it is isomorphic to the set of morphisms from B to omega. So we're basically saying that uh, the home object B of the object that contains all the morphisms going from B to omega, these can be represented as a subset of objects in B. This happens to be a natural isomorphism of two functors. In other words, yeah, because actually this is a set of sub-objects. That's what we call it, and it is as a family of monomorphisms. In other words, sub dash is a representable contravariate functor whose representation is the object omega. Yeah, this is already like I don't follow exactly because I have to recall what is our intuition of representable. Uh, but let's continue. So a topos is a category that is a Cartesian closed. It has all products, determinant object, and exponentials. has limits for all finite diagrams, and has a subobject classifier omega. This set of properties makes a topos a show-inverse set in most applications. It also has additional properties that follow from its definition. For instance, a topos has all finite colimits including the initial object. It would be tempting to define a subobject classifier as a coproduct of two copies of the terminal object, but we want to be more general than that. Uh, Topoi in which this is true are called Boolean.
They
What
are
is called
freaking
true?
booleans.
Yeah, they are freaking Booleans. The as a coproduct, right? So the subject object classifier is a coproduct of two copies of the terminal object. Well,
Which
yeah,
is
those are
literally isomorphic to a boolean.
yes. So now we're gonna go back to the terminology thing. So in set theory, a characteristic function may be interpreted as defining a property, a predicate. So a predicate is even is a subset of the even numbers of the natural numbers. In tuples, we generalize the idea of a predicate to be a morphism from object A to omega, which is going from chi and f. That is why omega is sometimes called the truth object. Predicates are the building blocks of logic. A topos contains all the necessary instrumentation to study that. It has products that correspond to logical conjunctions, coproducts for disjunctions, and exponentials for implications. And all standard axioms of logic hold in a topos except for the law of the excluded middle, which is a double negation elimination. Which I didn't know that, but apparently that is why topos corresponds to constructive or into intuitionistic logic,
Yep.
uh, which is a very interesting. It is a very interesting conversation because we're basically saying that in computer science we don't have binary logic all the time.
We do. It's just that it's not. How can I say this? Like, we're not saying that a proposition is neither true nor false. We're saying that we cannot prove that it is either true or false. That's the. It's a subtle distinction, but it's a distinction that you must make.
No, but I would say that 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 that's not the same as what we're talking about because what the author is saying is that the classical notion of the excluded middle is that a statement can be either true or false. But the problem is that in order to evaluate the truthfulness of a statement, in here we need to do something called computation. And a computation may not be able to necessarily give you that answer.
Because it may go into an infinite loop.
And that's why I said that using this terminology, we have a third state, which is called bottom. Uh, and that's basically why these types of non logics that are don't have the axiom of the excluded middle can be helpful for us in this particular case.
That's not.
That's not.
I wouldn't go to say that there is well, like, bottom is not really a truth value. It's the lack of a truth value. It's not really, like, how can I say this?
No, yes, it is not a truth value, but it is like an intrusion, an intruder, because you we cannot talk in the as we talked as this proposition here, because there may be a case in which we will not be able to get anything. That absence
Uh,
of anything, there's a name for that.
no, you can still believe that there is absolute truth, but the point is not whether there is absolute truth. It's whether you can prove that something is true or not.
No, no, but that's a different question. Your question is there truth or not? What the question of the author is, can we determine its value of true or falsehood or truthhood? Those are two different questions.
Those are two different questions.
The first question, which is more like a philosophical conversation, uh, we should have that conversation, but that's a different conversation than, okay, there is truth, but we have a constraint in our tooling in this case. in which we may not be able to say anything about it. There may be one. We may even go strong and say that there is, but we will die not knowing it.
Yes, because to prove that thing, you need to to complete an infinity, essentially.
Yes, and that's why. Well, my readings and studying tells me that people usually call that bottoms. Maybe that's wrong terminology. I don't know. But you can. But that's basically an intruder. Like instead of true or false, you may have bottom now, which is nobody knows. Um, and yeah, that's
Mm,
I was always interested to see why we would ever go to these types of logic systems, and now I have
uh,
a better understanding of that.
for the record, intuitionistic logic is technically more general than classical logic
Yes, well, yes.
because it makes fewer assumptions, essentially.
Okay. Okay. And then 1 hour and 15. So next up, we're gonna talk about this. Ideally next Thursday, and then the week after that, we're gonna talk about whatever 31 is. And then we're gonna finish the book, and we're gonna make comments about it and our thoughts about it.
You know what's
And
the greatest shame about this book?
what?
The greatest shame is that there are 31 chapters, but the first chapter is chapter 1 instead of 0.
Ah, classic Marinho criticism. Classic. I'm gonna finish the recording now.
Bye, future people.